Einstein provided a theory of how photons could explain the photoelectric effect. Millikan actually used that theory of Einstein to derive a measurement of Planck's constant h. This is the apparatus used by Millikan. He was one of the foremost experimenters of his day, and in fact he was the first to have measured the electron's charge E in his famous oil drop experiment. He's also the first to derive a really precise measurement of the Planck's constant h. That was done in 1961. I'll make a note that that paper has only 41 citations, and in today's world, that would be considered a not very successful paper. Of course, it happens to be one of the more notable experimental achievements of its day. Millikan's experiment took place inside of a vacuum chamber. That's because he needed the electrons to be able to travel around freely and not collide with particles in air. He also needed to study metals which were unvarnished or untarnished by oxidization, because we're talking about electrons that are being ejected from metals, and you had to truly know that the electrons weren't treated in some way on their surface by some sort of tarnishing, because that would perhaps alter the amount of ability for the electrons to get out of the metal. Einstein's equation, E times the stopping voltage is equal to hf minus W, predicts a linear relationship between the incident frequency of f of the light and the stopping voltage V0. The slope of that linear relationship is h over E. In other words, if V0 was the thing that's the dependent variable and f is the independent variable, putting V0 alone on the right, on the left-hand side of this equation, makes a slope h over E when this stopping voltage is plotted against frequency. E had already been measured by Millikan in the oil drop experiment, so multiplying this slope that he would derive from the present experiment by his previously measured E would derive a value for the constant h. In this experiment, which takes place entirely inside of a vacuum chamber, an electromagnet, denoted by the letters M and F in this apparatus, drives a knife edge forward, and the knife edge is denoted by K. That K is used to shave a metal layer off of the metal samples that are mounted on a wheel W. Those metal samples oxidize when they're in ordinary air, but once it's in the vacuum, Millikan used this knife edge K to start shaving bits of the surface off so you'd have a nice, clean, pristine sample. And he had several pieces of metal in there, like sodium or lithium or copper. The wheel W could rotate around. In fact, if he rotated it in such a way that it would face over to the right in this picture, he could shine light in through a little portal or a window at O. And when that light hits the metal, presumably it starts ejecting electrons. The electrons would be drawn over to a small mesh cage to measure a current, and that cage would be supplied a voltage using B and C, leads that go through the vacuum chamber. So in this way, Millikan was able to derive very precise values for clean surfaces of metals and study the electron current that comes ejected off of the metal by the light going through O. So here's basically what he saw. On the horizontal axis is the frequency of light passing through this window into the vacuum chamber. And you can see he was able to vary it from 4 times 10 to the 14 hertz up to 12 times 10 to the 14 hertz. On the vertical axis is plotted the maximum electron kinetic energy in electron volts that comes off of that metal. Basically, that's the stopping voltage multiplied by the electron charge, so it becomes a kinetic energy. And you can see that Millikan's data forms a pretty nice line. By eye, you could say I could put a line over that or with a ruler. He found that light below a frequency of 4.39 times 10 to the 14 hertz made no photoelectric effect occur at all. In other words, that's the stopping voltage, or that's the threshold for this particular metal to allow a current to flow. He also found that the current was not dependent on the intensity of the light, much in agreement with Einstein's suggestion that this is due to the particle nature of the photon, not the wave nature of electromagnetic radiation. As we said before, the slope of this graph is significant because it measures Planck's constant h. The slope is measured by the change in the vertical axis divided by the change in the horizontal axis. So that's delta E over delta frequency. That slope turns out to be 4.1 times 10 to the minus 15 eV seconds. In other words, a rise of 1.25 eV happens over a run of 3 times 10 to the 14 hertz. And that is in fact about right for Planck's constant. Millikan's work was also able to derive work functions of metal because that lowest threshold frequency, which tells us when is the electron current no longer going to occur, when does the photoelectric effect stop, also provides a measurement of the work function. Modern-day measurements of the work function for a number of metals are shown in the following tables, everything from aluminum on up to zinc and uranium. One derives these numbers by the lowest frequency for which the photoelectric occurs, multiplied by Planck's constant. Notice that these work functions are a property of the metallic species. Cadmium is different from calcium, is different from carbon, and so on. Although they are all pretty similar, they're all a few electron volts. They're quite similar because this is representing essentially the energy to pull an electron off of the outer shell of an atom. But notice that some of them are a little bit lower than the others. Notice that cesium and potassium and sodium in particular have the lowest work functions of all the elements in this table. If you consult the periodic table, you might see a trend for why this is so, why those particular elements are going to have the lowest possible work functions.